Okay, everyone. So let's get started. So this could be probably the last lecture I will teach you because next week will be the next professor. Okay. So anyway, let's continue. So we have talked about this problem, and well, I'm not very sure where did I talked in the last time, but I can quickly get a review. So the thing is, we are going to divide this one into the different angle. Okay, so that we can define a theta, and then we have the theta. We can calculate what is the electrical field generated by the d theta by treating it as a point. Okay, so that we have electrical field, and then we have the electrical field along the x direction, and then do the integration of the x direction over over the d theta. Okay, then you can achieve the final electrical field. No, should be dEx. Okay, and then the theta, depending on how you define the theta, could be from the minus pi over 2 until the pi over 2. Okay, so I think previously I have detailed introduced the method, and then by using the method for the d theta instead of dx, we can actually making the calculation much easier, because if you are using d theta, finally what's including theta is just cosine theta. Okay, and then cosine theta d theta, then that's just a sine theta. Then you put a number for calculation, and then eventually the ratio is pi over 2, which is about 1.57. Okay. Okay, so I think most of them has been introduced in the last class. Okay, so let's see another one. Okay, so in this figure, I have a small circular hole of radius and has been cut in the middle of the infinite flat non-conducting surface that has a uniform charge density of sigma, and there's a z-axis with its origin at the hole center is perpendicular to the surface. In unit vector notation, what is the electrical field at the point P at Z at a certain location? Okay, and then they already have given a hint saying, okay, see the equation, this one I use the superposition. Okay, the equation has been listed here. Okay, so if you are just using the very traditional way, probably you can integral. Okay, what is the electrical field generated by a line circular charge? Okay, and then you integral the electrical field generated by the line circular charge, and then from the R to the infinite, you will achieve the final answer, right? From the line circular charge, actually the electrical field has already been given in the PowerPoint, right? And then what you need to do is just the integration of the dEz, okay, and then from the R to the infinite, you will achieve the final answer, okay? Well, if you're doing this way, it is correct, but it is not that convenient. Okay, a more convenient way, we should take a look at the hint. Okay, we should say this equation and use superposition. Okay, so what is for this equation? This is the electrical field in the Z point if there is a charged disk to fill the hole. Okay, so from the superposition way, the electrical field generated by the disk plus the electrical field generated the plane with the hole, okay, which equals to the electrical field generated by by the total plane. Okay, so we wanted this one, right? But you know, we already have the equation for this one, and also for this one is just a very simple Gauss's law, right? So both of the other two are known, right? So that we can actually use the electrical hole with the hole equals to E for the plane minus E for the charged disk. Okay, for E for the plane, you know, we can just utilize the electrical field outside outside an infinite plane, right? So that we can just use the Gaussian surface. Okay, basically, if you take a look at cross-sectional way, that's positive charge. Okay, and then we can build a Gaussian surface. It's infinite, so we don't need to consider the top and the bottom surface. Okay, and you just need to consider the two-side surface. Okay, so that for the two-side surface, if you write down the Gaussian equation, that would be epsilon 0 EP and A, right? But there are two surfaces, so that's another two. So which equals to the total charge inside, that would be the sigma A. Okay, so you get A get crossed. So you will have the EP equals to, I know someone is asking questions, so let me just finish it here. Okay, EP equals to sigma over the 2 epsilon 0. Okay, let's see. Well, to find this PDF, okay, anyway, I have not uploaded that, but you know, these are all from the textbook. If you can just check the E version of the textbook, there is a problem number, so that you can know what is the problem is talking about. So basically, it's on your textbook. Okay, so there was a student who was raising hand, but I'm not sure where he is right now. Okay, so if you are raising hand, can you? This is built as a spherical with the radius of the r equals to a over 2 pi r squared. Okay, that would be equals to the total charge inside the Gaussian surface. Okay, so for the total charge, we can estimate from the Q1 and the Q1, and then the total charge inside would be just a ratio of the volume, right? Q1 over the volume of the total sphere, that would be 4 over 3 pi a cubic, and then 4 over 3 pi r cubic. Okay, so that you can use the r equals to a over 2, put inside, and then make a calculation. You will have the electric field for B point, which is about, as I calculated, is about 2.25 10 to minus 2 Newton Coulomb. Okay, so that's for the B. And for the C, R equals to A. Okay, so that would be just in this location, right? So that we can do the similarly. We can have the Gaussian surface, and then calculate the electrical field equals to the total charge Q, so that that will be epsilon 0 EC 4 pi A cube square equals to Q1. Okay, so that the EC is just 4.5 10 to minus 2 Newton per Coulomb. Okay, so that's for C. And then for D, D equals to R equals to 1.5A. Okay, let's see why is 1.5A. It's larger than A, right? But it is smaller than B, right? So that is somewhere here, right? So that will also do the same thing, build another Gaussian surface, spherical. Okay, then use the Gaussian equation, and that would be epsilon 0 ed 4 pi r square, okay, q. This equals to q1, right? Because the inside charge total is just q1. Okay, then ed, if you solve, that would be 0.02 Newton per Coulomb. Okay, so these are just the calculations, nothing special. But the thing is, you should find the correct radius and the correct, correct total charge. Okay, and then let's take a look at the E. Okay, well, someone is asking why B is not 0. Okay, B is not 0 is because the sphere is not conducting. It's non-conducting. If it is conducting, then EB should be 0. If it's not conducting, okay, then EB should have some value. That value was determined by the charge enclosed by the Gaussian surface. Okay, think about that. So there are two cases. If it is conducting, the EB is 0 and the internal charge is 0. If it's non-conducting, EB may not be 0. Well, in this case, because the charge was uniformly distributed in the sphere, it means inside there is charge. EB is not 0. Okay. Then let's take a look at the electrical field at E. Okay. R equals to 2.3A. Okay, so where is the 2.3? The B equals to 2A, C equals to 2.4A. So 2.3A is somewhere here. It's inside the shell. Okay, and then this shell is conducting. Okay, so well, that would be simple. If the shell is conducting, that means inside the conducting material, the electrical field is always 0, right? So for the electrical field of the E, it is 0. Okay, and then for F, R equals to 3.5. Okay, 3.5A is already larger than C, right? So it's outside somewhere. Okay, so if it's already outside, we can also build the Gaussian surface outside. Okay, but if you take a look at the internal charge, that would be Q1 plus Q2. But Q2 is actually minus Q1, right? So that Q1 plus Q2 equals to 0, right? So that for the F electrical field, it's also 0. Okay. Okay, someone is asking, is it a non-conducting if it is not mentioned in the question? It's not because not mentioned in the question. It is because it says there is a uniform charge. Okay, uniform charge, basically that means it is non-conducting, right? Because if it is conducting, it is impossible to make it a uniformly charged sphere, right? Okay. Okay, then let's take a look question for G and H. What is the net charge on the G inner and H outer surface of the shell? Okay, so for the inner surface of the shell, okay, because if you are want to know what is the electrical field at the point which is a little bit larger than the B, so that we can build somewhere here. okay, at a R, okay, let me just erase everything. If you build a Gaussian surface, that is the R is slightly larger than the B. Okay, so you build such kind of Gaussian surface. It is already inside the shell, so that the electrical field is 0, right? So that the total flux is 0, right? So that the total enclosed charge must be 0. Okay, so this enclosed charge means it has the Q1 plus Q in the inner surface. Okay, so that the Q in the inner surface is just equals to the -1. Okay, so that is the solution for E. Okay, and also you can see the Q in the inner surface is minus Q1, which equals to the Q2, right? So that in the edge for the outer surface, Q outer equals to Q2 minus Q in. That is also 0. Okay, so in this case, all the charge in the outer shell is concentrated in the inner surface, nothing in the outer surface. Okay, so let's say the question, so the charge is evenly distributed on the whole sphere, but not on the sphere surface. That's correct, right? The sphere is uniformly distributed with charge. That is non-conducting. And if it is conducting well, it's not in this problem. That could be purely on the spherical surface. Okay. Okay, so let's see another question that is also related to Gaussian surface. Okay, so this figure shows the cross-section through a very large non-conducting slab of thickness of D and uniform volume charge density. So what is the magnitude of the slab's electrical field at an x-coordinate at 0, at 2, at 4.7, and at 26? Okay, so so this is basically a slab, but that is can be considered as the infinitely large. So because it says very large, then we can just assume it's infinitely large. Okay, so basically this is a huge wall. Okay, and we are taking a look at the cross-sectional way. Okay, now when we say that very large, that's basically say, okay, the size is you can treat it as okay. So here for the electric field at the 0, right? Basically we can just say it's 0. Okay, one thing is by symmetry, another thing is you can build a Gaussian surface, right? Basically this Gaussian surface is overlapped at 0 point. Okay, and then enclose the charge is 0. Okay, so that the electrical field is 0. For the x coordinate of the 2, right? You know, for the thickness is and then x the origin is at the center, so that this thickness, the slab's range should be coming from minus 4.7 until the 4.7 meter, right? Okay, so that if you are say 2 millimeter, that is inside the slab. Okay, so that we want to field. Okay, So the Gaussian surface, okay, this is Gaussian surface, and we don't need to care about what is on the top and what is bottom. That is because it is symmetric, right? So the electrical field is parallel, and we only talk about the two vertical surfaces, okay? So that we can use epsilon 0 electrical field B, because there are two surfaces inside. We already know the charge density rho, and then we can make the rho multiply with the thickness, okay, two, okay, and then multiply three. This is by my calculation, right? You can, if you have time to calculate, you can check. Okay, so 4.3 10 to minus 7. Okay, and then C for the 4.7 millimeter. 4.7 millimeter for X is actually on the boundary. Okay, so that you can do the same thing. You can build the Gaussian surface, right? And then you can calculate what is the electrical field from the Gaussian equation. Okay, basically you will achieve the same equation, but with a different number for the x coordinate, right? Okay, so that you can do the same thing, and then the final answer is 1.10 to minus 6 Newton per coulomb. Okay, and then D, 26 millimeter. Okay, for the 26 millimeter, it's already outside, right? So you should go outside somewhere, and then build the Gaussian surface, and then check the included charge. But the included charge, please pay attention. Say, okay, I only have the total thickness of 9.4. Okay, so that in this case, the ED, if you derive, that would be the D rho over 2 epsilon 0. Okay, and then it is still about 1.6. In fact, when it achieves is on this surface, the electrical field will be a constant. Right? You can think about that. Okay, outside. Okay, so these are the problems for the Gaussian's law. Right? As you can see, for the Gaussian's law, what the problems will always have some kind of symmetry. The symmetry is either the spherical symmetry, either the cylindrical symmetry, or either the planar symmetry. Right? And then the calculation won't be very complicated. Right? But the key thing is how could we build up the Gaussian surface properly? Okay, so that we don't have too much calculations on that. Okay, so this one is about the electrical potential. And the figure shows the non-conducting load of the length L 6 centimeter, okay, and a uniform linear charge density lambda. Assume that the electrical potential is defined to be V equal to 0 at the infinity. Okay, so what is the V at the point P at the distance D equals to 8 centimeter along the wall's perpendicular bisector? Okay, so let's solve this problem first. Okay, so for this problem, well, we already have the v equal to 0 at the infinity, right? So that is actually consistent with the Coulomb's equation for the point charge, right? Because in that equation, you should make the v equal to 0 at infinity at the beginning, okay? And then in that case, we can just calculate the total potential by integrating also this line. Well, you can, I mean, you can basically divide it into many sections and treat everyone in the as the dx, okay, as the point charge, okay. And then you calculate how much potential you can generate it from the dx. Okay, so in this case, you can just say, okay, dx, and the distance is x, and then you build a distance of r, and this r equals to d squared plus x squared and square root. Okay, so that totally the potential generated dV is just k lambda dx, okay, over the dx x squared. Okay, and then we have the v, total v, integral with the dv. Okay, the very good thing is, for the potential, we don't need to consider too much about the direction issue, right? It's a scalar. So, but you still need to pay attention to its range, okay? So that let's firstly take after the constants. Okay, the range should come in from the minus L over 2 until the L over 2, right? And then that would be dx square root d squared x squared, okay, and then do the integration. Okay, so how do the integration? We it's a mathematical problem. Probably can just check with integral table. But anyway, the final answer is relative to a line. Okay, line, then square root L squared plus 4D squared plus L, and then L squared plus 4D squared minus L, okay? And then the final answer here is about 0.0467 volts, okay? Let's see the question. Can we find a solution in the PPT? Well, I will not upload this PPT. This is just a problem from the textbook. Okay, so you can refer to your textbook, and I already have the problem number. Okay, so you can just check that. And for the solution, I have already give you during my lecture, so that it is also not necessary. And also for some solution, it's already given in the textbook solution section, okay? So you can calculate by yourself and check. Okay, so let's see for the question B. Okay, the figure shows an identical rod, except that the one half is now negatively charged. Okay, one half was flipped over. Okay, becomes a negative. Okay, both halves have a linear charge density or magnitude or whatever, and well, this charge density is different. Okay, and with v equals to 0 at infinity, what is v at the p? Okay, for this one, if you do everything step by step, you can do the same thing, right? Divide it into many dx. For each dx, calculate what is the potential generated here. Okay, but in the right half is just a flip over, right? And then you can you can calculate what is the total potential voltage. Okay, but we have some easier way. Okay, so what is the easier way? Well, you can check. You can divide them into many dx first, but when you are dividing the dx, you can find a symmetric location that you can have another dx. And then you can calculate what is the generated voltage at P. So that would be the dV k lambda dx plus R. Okay, so if from the left side, it's this value, and in the other side, if I say dV2 equals to minus k lambda dx R, right? The reason it's a minus because that is the charge charge's sign was flipped over, right? And also for the R, the value is the same because the symmetric. Okay, so that if you are adding the dV1 plus dV2, you just get a 0. Okay, and this is highly symmetric, right? So that if you integral from the minus L2 until the L over 2, you will eventually achieve a 0 in potential. Okay, so that's one method we can do. Okay, another method we can do is we can check is the electrical field in the P. Okay, the electrical field generated by dx in the left would be along this direction, right? Somehow like this. Okay, that one generated by the right part, so it's a negative charge, will be along this direction. Okay, these two should have the same magnitude, and also the angle between the horizontal line should be the same. Why it is the same? Because they are symmetric. The only thing different is the charge sign was flipped over, right? So if you calculate the amount, that should be, if it is positive, that should be like this one. But it is flipped over, so it turns in the other way. But its angle to the horizontal line should be still the same, right? So that the total electrical field on the P must be horizontally along this direction, around the right direction. Okay, so now if you think of any point that was in the same z-axis of the P, okay, if you are saying this is the z-axis, if any point in the z-axis, okay, the electrical field are always pointing in the right, okay, until the infinite. Okay, what does that mean? That means if you move a charge, test point charge, coming from the infinite location to the P, right? What you can do is just along the z-axis, right? And then when it is along the z-axis, its moving direction is always perpendicular to the electrical field. Okay, what does that mean? That means there will be zero work done to compensate the change in the electrical potential energy. Okay, so that is no change in the electrical potential at all. Okay, and also because the potential at the infinite is 0, right? So that the Vp, the potential at the P, is also 0. Okay, so that is another method you can do to calculate to evaluate the V at the P. Okay, and then the last question is the potential at the P positive, negative, or 0 if the P is moving in the plane of the figure by distance of the L over 4 C upward and D leftward. Okay, let's see what is when it is moving upward, what will happen? Okay, we already know in the z-axis the electric field is along um, is going to pointing to the right direction. Okay, so if the P point is moving upward, right? So that is still moving perpendicular to the electric field, so that the potential of change is zero, right? But if you go with the leftward, right, that is actually against the electric field, right? So that we already introduced for the electric field, it is always from a high potential to a low potential, right? So that is against the electric field. That means it moves to the higher potential. Okay, you need to make some work to compensate the electrostatic force, right? Okay, so the work must be done. And then in that way, the potential would be increased. Okay, so that is the way, well, because they're not asking how much. Okay, so we actually don't need to calculate. We just need to do the analysis. Okay. Okay, there are not so many times, so let me just skip to another one, which is about the capacitance. Okay, so this figure shows the capacitor of the plate area A and the plate separation 2D, and left half is kappa 1 in the dielectric constant. Right part is kappa 2 and kappa 3. Okay, they are stacked together, right, in the right part. Okay, so what is the total capacitance? Okay, well, there are also two ways to solve this problem. Okay, one way is more traditional. That means, okay, you can build the Gaussian's law for kappa 1, build the Gaussian's law for kappa 2, build the Gaussian's law for kappa 3. And then you list the equation for including the dielectric constant. Okay, so basically the ds equals to the root s. Okay, ds is displacement vector, okay, and then which equals to the epsilon 0 kappa whatever, okay, and then e. Okay, let's see if it is kappa 1 e1, this is d1 root 1. Okay, root 1 means the charge density at the left side, okay, s. Okay, so that you can solve for the e1. Okay, e1 is just root 1 over the epsilon 0 kappa 1. Okay, so that you can also solve e2, solve e3, but of course for the e2 and e3 you have the same charge density. e2 kappa 2, e2 root 2, epsilon 0 kappa 3, right? Okay, and also the total voltage equals to 2dE1 equals to dE2 and dE3, right? So that you can actually solve what is the relationship between the root 1 and the root 2. And then the total Q equals to A over 2 root 1 plus A over 2 root 2, right? So that you can calculate what is the total charge, okay? And then the C equals to Q over the V, right? So you can do the derivation by yourself. The derivation steps are quite complicated, so I won't do here, but I can give you the final answer. It is epsilon 0A and 4 over the 4D and kappa 1, kappa 2 plus kappa 1, kappa 3 plus kappa 2, kappa 3. Okay, and then kappa 2 plus kappa 3. Okay, so that is 2 times here. Okay, so that would be the final answer. But there is also another very simple way. Okay, so if you don't care about the duration for the displacement, right? So that you can actually treat it as 3 capacitors. The left capacitor is half of the area, and the dielectric is kappa 1. And then in the right side there are 2 capacitors. One is kappa 2, one is kappa 3. Okay, so kappa 1 is with the 2D but the half area. Kappa 2 and kappa 3 is the half the area, but with the only D, but there are kappa 1, 2, kappa 3. So that you can actually calculate what is the individual capacitance on the 3 capacitors, and then make a serial connection between the C2 and C3, okay, 2 and 3, and then calculate what is the total serial connected capacitance, and then make the parallel capacitance with the kappa 1, C1, okay, so that you can actually calculate the final capacitance, which will make the same answer as this one. Okay. Okay, so anyway, so we should finish now. And well, I highly appreciate being your teacher and talk about electromagnetic courses for the first 1/3 part. Okay, and so the next week will be another professor. Okay, and if you still have questions, especially by my part, it's not necessarily by my part. It's okay if you have the following question to talk to me. Okay, you just feel free to email me. I will usually just reply you in 24 hours. Okay, and thank you so much. And hopefully, I guess I will see you in the final exam. Okay. Okay, so I'm still staying here if you have questions. Okay, so let's see. Can you explain 46D again? Okay, let's see. I'm confused how to calculate the Q with the ratio. Oh, which problem is 46? Solid sphere. Do you mean this equation? Okay. Will the Q2 affect the E field? Of course, the Q1 and Q2 affect the E field. Okay, but if you are saying for the D, okay, which is the R equals to 1.5A. In that case, you know, it is outside of the A, but it's still inside of the B. Okay, so that you can build the Gaussian surface. Okay, and then calculate its flux. Use the epsilon 0 E surface area. Okay, 4 pi A square, and then the right part is the charge inside. So that's a Q1, right? Probably your question is whether we should consider Q2, okay? If you are doing the integration of the Gaussian surface, right, you should not consider any charge outside of the circle, okay? Outside of the surface. You should only consider the charge inside of the surface, okay? So the thing is you don't need to consider Q2 here, okay? Okay, the question is the minus VE charge accumulated at the inner surface of the shell? What do you mean by negative? I mean, is minus VE. I'm not sure what is minus VE, but anyway, the charge, the negative charge was truly accumulated in the inner surface of the shell. Okay, so as I said, for the G, okay, so this is actually for the G. Okay, G, for the G, if you build a Gaussian surface that is right a little bit larger than the B, okay, so that you have the electrical field at 0. Okay, then electrical field is 0, then the total charge inside is 0. Okay, that means all the negative charge Q2 was accumulated in the inner surface, so that the total charge could be the 0. Okay, so you will achieve the inner charge just equals to minus Q1. Okay. Okay, question is, so the electrical field at R equals to A and R equals to 1.5A are the same because the total charge inside the area are the same. No, they are not the same. Even though the total charge inside the area is the same, but if you are calculating the total flux is equals to E multiplied with the area. The surface area is different because the radius is different, right? So that the electrical field is different. Okay, so the general equation here is R squared. Oh, did I use the A square? Sorry, I should not use A square. Should use the R square. Okay, but one R is A. Another one is 1.5A, right? So that if you see the difference in the R, then there must be difference in the electrical field. Okay. Okay, see if you have questions. Stay a few minutes. Enjoy my last few minutes. Thank you. Thank you, everyone. Conducting. Okay. Probably I can make a. Okay, let me go to my whiteboard. Okay. Okay. Conducting objectives. Inside the conducting objectives, the charge can freely moving anywhere. Okay, so that is the key. So if in this case, if there is a charge generated, taken by the conducting material, okay, what's really happening is there will be no electrical field inside. Okay, so because if there is any kind of electrical field inside, then the charge will freely moving because if there is a charge, there's any electrical field inside, the charge will freely moving to the other location. And then this charge and the electrical field, they can generate a counter electrical field to compensate this electric field, right? So that the end up electric field will be 0. Okay, so that inside the conductor, no electric field. And also because there is no electric field, so there is no charge in the middle of the of the conductor. Okay, because if there is some kind of charge inside, that means due to the Gaussian's law, you can have the electric field going outside. Okay, but that would be against what we're saying. We have no electric field. Okay, so that for the conducting material, electric field inside is 0. Okay, and all the charges are on the surface. Okay, so this surface, well, sometimes could be the inner surface if you have some included some material taking charge, just as what we said for the problem. Okay, but anyway, it's in the surface. Okay, but for the non-conducting, it is not necessary. Non-conducting material, the charge could be anywhere, right? And it could also be saying someone take the negative charge, some area take the positive charge. That could also possible. Okay, but the very common we use the non-conducting material is in the problem is we have the uniform distribution. Right. So that is a very common one, because if you can have uniform distribution, we can just use a charge density to represent its charge distribution. Okay. Yeah, conducting charge is only on the surface. Non-conducting charge could be anywhere. It could also be the surface, right? Okay, but could be anywhere. Okay.
Okay, let's start today's tutorial. Today we will talk about the third tutorial, and it's more about the electrical field and electrical potential, which help you to review the content you learned in the class. Okay, can you see the screen? Tutorial 3, PowerPoint. You can find the can you see the screen now? For the tutorial PPT, you can find in the Blackboard. We will upload the PowerPoint after the tutorial. Okay, first, we have an example for the relationship between the electric field and the potential. So this is the first example. So I can give you about 2 minutes to review this. For this question, we need to calculate the electric force on the electrons. So they have given us the potential distribution, actually, like here, for the x direction and y direction. And so the question is to calculate the electric force. So how to get the electric force? Maybe we can remember that the force is equal to the Q times electrical field. And the most important thing is to get the electric field. And we have know the electrical potential here. So the important thing is to how to use these two guys to calculate the electric field. So maybe there have some hints. Okay, from what you learned in the class, that we have know the work that the electric does can be expressed by the minus Q0 times dV, where V is the potential and Q is charge. So it can be also expressed as by the electric field, which means you need to times the electric field with its path. But there is one thing you need to mention, that the electric field is a vector. So we need to consider the angle, the theta, with the path. So therefore we can get this equation. The potential, electrical potential times Q is equal to the Q times E times the path. So you can see that the electric field is equal to deviation of V of the potential to the path. So is a so we can get the relation between the potential and the electric field. So you need to take the derivative of the potential to calculate the electric field for the Ex and Ey, because this is a 2D. For this question, this is 2D. We only need to calculate the Ex and the Ey, and they are with the derivative, they are all constant. They are all the constant. So it's easy to calculate the electric field for the Ex and Ey, and then express as expressed with the direction. Then use the F force equal to the Q times E and get what we want. Okay, so the most important thing is to figure out the electric force, how to get the electric force, because we know the function, the force equal to the Q times E, and how to get E. E has a relationship with potential, with the electrical potential. So and use this relation, we could calculate the force. Is that clear? Do you understand this problem, this question? Any response? If you have any question, you can type in the chat box. This is -7. Let me see. Yes, we because you need to use the work that they have two different expression. If this is equal potential surface, so the work can be calculated by the charge and the difference between the potential. So this is a definition of the work that the electric field does. And for another thing is to use the definition that F times S, W equals F times S, the force and the path. So for the force is in the electric field is equal to the Q times E, because E is a vector. So we can get this, the expression like this. This is just two different expressions of the work, but they are the same, so we can connect them together. So E is the slope of the graph. Yes, because here, because this is a potential, right? And through this equation, we have got the Ex can be calculated by the differential of the potential with X and Y. So they have the relationship. So so it's the slope of the graph in the electrical potential. Because it can be expressed as the differential with the potential, electrical potential. So it's a slope. So integrated of the... Actually, no. F equals Q times E. This is a force. This is a force. And this is an electric field. No, not integrate. I mean, E equals dF over dQ. Oh yes, you can think about you can understand that. Because the force is related with the charge. So you can, because dF is, you can think as only a small, only a dQ. The charge with the dQ in the electric field have the force of dF. You can think about this. Okay. For the next one, this problem is related with the electrical dipole. So the dipole moment in this question, we need to calculate the magnitude of the dipole moment. So you can look about this question. I'll give you about 1 or 2 minutes. And if you have any questions about last question or this one, you can type in the chat box. For the Marcus, can you understand what I said? Well, here's this question. For the dipole moment is equal to the charge with the distance of the dipole. So you need to know this concept. The dipole moment can be expressed as Q times D. Q is equal to the charge of the dipole, and D is the distance between the dipole. It's only one scale for the horizontal axis. You can imagine in this question, you can imagine that this is only one D situation. There's only one direction. And for the kinetic energy, okay, the initial kinetic energy is 100 eV. So when it arrived at the because IS is 0.1 meter, so when it arrived about 0.02 meter, all the kinetic energy has been exhausted. It means that at this point, the energy should be 100 eV, the potential. So first we need to calculate for this problem, we need to calculate the potential. The potential in the electrical dipole situation. So for the point P, actually we can calculate separate because the potential is a scalar, not a vector. So you can just plot them together and calculate separately. So for the potential at the point P, we can find that for the positive charge, the potential can be expressed as this one. As this one. And for the negative charge, the path can be expressed as R minus. Because they have a difference between the R plus and R minus. So we can just simplify the expression. If the D is much little than the R, much smaller than the R, we can use we can use this difference as D times, because the other things can be eliminated because they are the same distance, and the only difference is D times cosine theta. And R can be simplified as the same if the distance is much smaller than the R. So the potential can be expressed. The potential of the electrical dipole at the point P can be simplified as this expression. And for the electric moment, we have defined it that the electric moment is equal to the charge times the distance. So expressed the exact potential by the dipole moment, we can get this expression. Okay. So we have known that the energy at the R equals to 0.02 meter. All the energy is transferred as a potential. And the energy for at this point, we can express as the Q times V because we have known the V. The expression has been calculated here. So use this energy equals 100 EV and R equal to the 0.02 meter. We can get the magnitude of the dipole moment, P. Okay. Any question? The most important thing is to use the equation of the potential due to an electric dipole. Okay. So for the example 3, it's also about the electric potential. You can read the question and for about 1 minute. And then we have known that potential is a scalar, so we can calculate one by one, separate and then just plot them together to get the final expression. So this question it can be simplified as equation as the example 2. To put the dipole separate and calculate one by one to get the answer. For this question, because just as what I said, the electrical potential is the sum of the contribution of the individual sphere, which means that you can calculate the potential one by one because it is a scalar. So first get the potential of the Q1 and get the potential of Q2 on the halfway between them, so they have the same distance. And we have know the potential is equal to the Q over 4 times pi times epsilon 0 times R, where R is the same in this situation, so we can just simplify it by use V1 times V2. And because the R is the same, so they can combine together to calculate the potential of the halfway. So for the question B, it's the same for the first one, just change the distance between the two spheres. The first one distance is R, is the radius of the first one, and at this point, the distance between this point to the Q2, sphere 2, has the distance of D minus R. So there has a little difference of the R for the V1 and V2. So we can express them separate. This is V1, this is V2. So this can be also easy to calculate the potential. The question 3 is the same. You only need to change the distance, the distance of V1 and V2, because the site is different. It's on the surface of sphere 2. So for the V2, the distance is equal to R, and for the V1, this is equal to the D minus R. This is the only difference. Okay. Any problems for these two questions? Maybe you can go through the example 4, and if you have any questions, you can come up in the chat box. In this question, you need to pay attention to the cylindrical capacitors. First, we need to know the capacitor C1 and C2. So how to get the capacitor of the cylindrical capacitors? So we can use the Gaussian law. The inner and outer plate. It's only a simplified plot. So it didn't plot the cylindrical. It's only use a simple Here is the inner. Oh, this is only a sign to express its capacitor. It didn't draw the cylindrical capacitor here, but you need to pay attention that is a cylindrical capacitor, and here, actually this is inner and this is outer plate. So first we need to know the cylindrical capacitor and how to calculate how the capacitor of this. First we can use the Gaussian law Q equals to E0 times electric field times area. And in this one, the area can be calculated as 2 pi times r times L, where r is the radius and L is the length of the cylindrical capacitor. So we can calculate the electric field in the capacitor. And the equation we have introduced in the first example, that E equals minus V, the differential of the potential with the direction. So here we can use the integration expression to get the potential. And here is the expression of the potential of the cylindrical capacitor. What is L here? L is the length because it's a cylindrical shape. So it's the height. You can say it's the height. L here. And this is a front view. And this picture is a front view of the cylindrical capacitor. So you can see that the air is here. It's about this one. So with this equation, and we have known that the capacitor can be expressed as the Q charge over V. So the capacitor can be expressed as this thing. So we have got the expression of the capacitor of C1 and C2. And you can see with the inflation, actually the capacitor, because C is also with epsilon s over d. First, we have know the C1 and C2, and the total capacitance because it's in a series. So we can calculate the total capacitor. And for the charge, we can know that the charge, because it's in a series, actually the charge of each capacitor is the same. So we need so for the charge Q equal to the C times V. Actually, not this expression. Is C equals Q over V, and Q equals CV. So we can get the charge. But you need to pay attention that for the inflation, due to the inflation, the length B, actually the radius B has changed. We need to recalculate the capacitance of the total capacitance due to the change of the B. And then for several minutes after the adjustments, it's reached a balance, and some charge has been moved, and some electrons have been came in to keep the balance. And because the charge under this situation has changed, we can see we have lost some charge after the inflation due to calculation. Because it's a positive plate, the loss can be imagined that they have met the electrons and combined together. So the electrons should come to the platelet. So the suffer decrease. So for the point P, so the electrons should come at the right forward side. The point in this problem is to first calculate the capacitor. Use the Gaussian law. The second is to calculate the total capacitor, because in a series, you need to pay attention to the total capacitor, the expression. When you met the inflation, you need to reach a new balance, so the capacitance should be changed, and you need to calculate the change, the total capacitor, and get the total charge difference, and then we can figure out the way they move towards or forward through the point P. Okay, and for the last example, this one is also related with the capacitance. And for the capacitance, and its definition is about the epsilon with the area of the capacitance and the distance between the two plates. In this problem, and for the energy of the capacitance, E capacitance, can be expressed as 0.5 times C times VI square. So this the equation what we need to use to solve this problem, solve this example. First, they ask us to calculate the potential difference between the pairs. And then they need to upload the stored energy and the final energy. Then the work we need to use. Okay. For the first one, because the definition for the capacitor can be expressed here. So the charge Q equal to the CV, C times V. And the distance of the pairs, dF, has been given. So when the pairs are pulled apart, the charge didn't change. So we can use this relation. To get the VF, to get the potential. Why can we use the Q? Why can we use why can we imagine that this is the same Q? Because there is no other way for this charge to get out. Because we have in this problem, they have disconnected from the battery, so the charge can't run out. So it should stay in the plates. So the Q should be the same. But when we change the distance of the plates, the capacitance has changed. So the potential should also be changed. And by using the definition, we can calculate the difference of the potential. It's changed. And the energy stored can be easy to calculate by using the equation here. And also, the final energy stored can be calculated at the same expression, but this should be the VF, not the VI, and the C should also be changed. To use this relation, we can easy to calculate the final energy. You can see that the energy has changed, and this work needs to be done by the outside. We need to use some work to pull the plates apart. So the difference is the work we need to be done. This is this question. So any problem? Any questions? For this too. Oh, sorry. How the change in distance changes the voltage. Oh. Here. Here, because the capacitors can be expressed by the charge and the potential, right? And the capacitance can be also expressed as the epsilon A times the area over the distance. But this is the definition. But actually this expression is the definition of the capacitor, and this is only the reflection. When the distance changed, the capacitor has changed. And after the capacitor changed, and the Q is the same, and the charge is the same because the charge have no way to run out, so the charge is the same. And the capacitor has changed and the charge is the same, so the voltage need to be changed. You can use this expression to calculate the capacitor, but this is not the definition of the capacitor. So if connected to the battery, if it's connected to the battery, the voltage should be the charge should be the change. Yeah, the voltage will be the same, but the charge need to be changed. Yes, the voltage will be the same. Smaller charge? What do you mean about a smaller charge? Oh, if the distance with battery connected situation, the voltage should be the same. And if the capacitor decreased, the charge should be decreased as well. If it's increased, the charge should be increased. Okay, you're welcome. Any other questions? If there is no questions, today's tutorial has been finished. If you have any problem, you can email us. Okay. Today's tutorial has finished now. You're welcome.